binaries apparently.
Yes.
Yeah.
Binary stars in general.
Thanks.
Thanks so much for the invitation to come over. I've been hanging out at the KITPU program on white dwarfs. And I'm so tired of hearing about white dwarfs that I thought I would talk about black holes for a little while. That's actually not true at all. It's been a really fun program. But yeah, it's been awesome to like see real telescopes. I'm a theorist by trade, so everything feels really dramatic and fun here. And today, yeah, I just want to go through a few recent fun results of ways that we're trying to understand how black holes form, primarily in binary star systems. Before I start every talk, I like to be dramatic to make sure everyone's awake. And stars are either a critical component of astronomy or a limiting factor of astronomy. And that really comes into play literally in basically every part of astronomy. So for things where it's pretty obvious, things like star and planet formation, binaries are the driver of basically whether or not you make planets or not. Compact objects, stellar evolution, these ones are obvious. Multi-messenger astrophysics, also pretty obvious. But in exoplanet populations, binary stars are often the most annoying things in your sample. So if I understand binaries, then it's mutually positive for both of us for me to understand binaries.
Well, you have a radio galaxy where, what do I need to know about binaries? Oh, no, that's not, is that a radio galaxy? No.
Binaries drive a lot of the feedback in galaxy systems because the massive binaries have all this ionizing radiation, and binary star interactions can actually prolong the amount of time that you have this massive star radiation going on by at least several million years.
Okay.
So that's fun. Similar things also in resolved stellar populations. Most resolved stellar population work treats everything as singles, and that adds a lot of systematics. Similar things happen when folks are, for example, looking at streams in Gaia data. Their biggest false positives come from binary interactions within the stream, where they could think that there's a dark matter clump, but actually it's a binary interaction that's driving that peculiar motion. So really, everyone should be pretty interested in binaries if they're interested in doing astronomy at all. Good. Okay, so we're all on the same page there. What I actually want to talk about today are the things that I think about as major uncertainties in binary evolution as a theorist. I'll tell you about how I use population as a tool to connect binary evolution theory and data for binary stars. And then hopefully we'll have a fair bit of time left over to do a deep dive into black hole formation in stars using gravitational wave and EM observations. So first, I am a theorist, but I'm kind of like, I sit a little bit in between phenomenology and theory. I don't run stellar evolution codes that do stellar evolution calculations in real time. Instead, I run population synthesis codes, which take two stars that are fits to single star evolution tracks. And then at every stage in the binary's evolution, they ask, are different binary interactions going to change either the stars themselves, how the stars are evolving, or how the orbit evolves? And so there are sort of, if you take two massive stars that will eventually make a binary black hole, there are several tracks that you can take, and I'm going to walk you through the primary tracks. So first, we're going to start out with a massive zero-age main sequence binary. There's going to be something like maybe 40 solar masses and 20 solar masses, but really anything above 20 solar masses, you're in black hole formation territory. The more massive star is going to advance off the main sequence. It's going to fill its Roche lobe. When it does that, we have physical prescriptions for whether or not the star filling its Roche lobe is going to remain in a stable mass transfer configuration like this. In that case, the orbital evolution doesn't happen on short enough timescales that the mass transfer becomes unstable. So you have a nice few million year long stable Roche overflow situation that leaves behind a strip star and a massive star. In this case, you can often find mass ratio inversions where now this system is actually more massive than it started out with, and now this is the less massive star. Pretty rapidly afterwards, that strip star is going to collapse to form a black hole. When that black hole forms, there might be a direct collapse. In that case, we don't think that there will be a very strong natal kick in the system. If there is a supernova that leaves behind the black hole, there could be a strong natal kick, and that kick is going to shape the size of this orbit and the eccentricity of that orbit. Eventually, you're going to go along a similar pathway where the initially less massive star advances off its main sequence as well and can go into a stable Roche-Lobe overflow interaction again. This would be a fairly rare situation, I think, just because if it's a massive star progenitor, we actually don't know of very many black hole binaries that have Roche overflowing companions to them in the X-ray binary catalogs that we have. Most of them are actually in a detached state that are closer to this. So most of our high mass X-ray binaries are in that state rather than a stable Roche overflow. Once the Roche overflow detaches, you're again left with a stripped helium core in a black hole. That stripped helium core will form a black hole. And then you've got a binary black hole that's only going to evolve due to the emission of gravitational waves. The emission of gravitational waves will shrink and circularize the orbit until you eventually get a merger that's observable by detectors like LIGO. So that's one channel. You could instead come off of this branch and have that mass transfer go dynamically unstable. In that case, we think you go into something called a common envelope evolution. The dynamics of a common envelope evolution happen on much more rapid timescales than the million-year thermal timescale mass transfer that you would see in a stable Roche overflow configuration. They also result in much closer binaries. And that's because as the two cores, or the black hole and the stellar core here, orbit through the envelope, we think that there's some process by which drag shrinks that orbit and deposits the orbital energy into the envelope to unbind that envelope, leaving behind a very usually quite short period binary afterwards. We have not conclusively ever seen common envelope events. Some folks are looking for them as these luminous red novae, but the luminous red novae candidates for common envelopes are coming from much lower mass stars than anything that's going to make a black hole up here. So this is a super uncertain phase of evolution that has a lot of impact on what we get out of our binary population studies. Eventually you make your binary black hole. As you can see, it happens a lot faster because of if you have two stable Roche overflow mass transfer interactions, that's going to occur over much longer timescales. And this can lead to mergers on shorter delay times. Cool. That's one track. I'm going to go a little bit faster through the other tracks just because we basically covered everything that can happen. So if instead the primary advances off the main sequence and the mass transfer becomes dynamically unstable, you go straight into a common envelope. That's going to make your evolution proceed a little bit quicker. You can again have potentially natal kicks shaping the size and eccentricity of this orbit. You can go into a stable mass transfer, strip star, binary black hole merger, or a double common envelope system where both stars go into an unstable mass transfer phase, binary black hole, and merger. So these are basically all of the ways in a standard isolated binary evolution scenario that you can make a merging binary black hole in the age of the universe. There are many, many, many uncertainties that abound here. And so what I want you to take away from this are first, Roche overflow mass transfer physics is the dominant driver in the uncertainty of how binary star populations work. And it's the dominant shaper of stellar remnant populations of all kinds. Any binaries containing white dwarfs, neutron stars, and black holes that are close enough to merge or emit gravitational waves have gone through these mass transfer episodes, and they're super uncertain. But if we can observe those stellar remnant populations, maybe we can back out what's happening in that Roche overflow phase. The other thing that's really important in the formation rates and characteristics of neutron star and black hole populations is this compact object formation mechanism, which may or may not impart a natal kick when that compact object is formed. The way that we incorporate all of these uncertainties is something called binary population synthesis. And what binary population synthesis does is basically provide a means to understand all of the uncertain physical processes in binary stars, and basically watch how stellar populations are shaped under every set of assumptions that we can come up with. There are, I should highlight, many, many other assumptions other than Roche overflow mass transfer and compact object formation mechanisms that we put in our codes. We treat things like stellar winds, tides, magnetic braking, we run the whole gamut. So there's a lot going on under the hood other than just these two things, but these are the dominant ones. So the majority of what I spent my time doing at Northwestern was vamping up this code called COSMIC that is a binary population synthesis code. It's designed to make large populations of binary systems. We originally developed it with compact objects in mind, but it can do any kinds of stars at any stage. One thing that we're really proud of and excited about is that it is integrated into the globular cluster dynamics code CMC, which is hilarious because there's a CMC next door. It's a different CMC. CMC does globular cluster dynamics evolution, but actually incorporates the exact version and physics of COSMIC, because COSMIC is functionally a Git submodule in the code. So we know that if we run isolated binary populations and globular cluster populations, we are doing apples to apples comparisons, whereas previous to this paper, all comparisons have been someone runs a code, they compare to isolated binaries, but the underlying stellar evolution is different, so you're kind of comparing two moving targets. So that's something that we're quite excited about. If you are interested in binaries for any use at all, COSMIC is the easiest way to get a population of binaries at any age in metallicity. You can download the code and run a population of binaries in about 10 minutes. You'll get about 10,000 binaries, including the install time. So it's very, very easy to use. Good. I want to quickly acknowledge this lovely team of people who put a bunch of work into actually making COSMIC be as usable as it is. It was lots and lots of years of work, and especially the people on this top row, we spent an enormous amount of time getting the codes to work together and building our documentation. So far, since COSMIC's paper release in 2020, we have 52 studies. You can see, obviously, merging binary black hole populations are very popular these days. It's because there's something called gravitational waves that were recently detected, and everyone wants to know where they come from. The other thing that I want to quickly highlight is that everything that I'm showing in green, these are actually studies that contain no COSMIC developers on the author list. So that means that people can actually use the code without having to call us and have us help them run the code. As I said, it does all kinds of stars. So COSMIC has been used to study blue stragglers, common envelope events, accreting and non-accreting double white dwarfs, X-ray binaries, galactic center events, and today I'm mostly going to focus on detached black hole plus bright star binaries and merging binary black holes. If you are interested in anything else related to white dwarfs and neutron stars, the space-based gravitational wave detector LISA, or survey selection functions or open software, do feel free to reach out and email. I'm always happy to chat about those things as well. Okay, so let's get into science. We live in the future. When I started my PhD in 2013, a nuclear physicist came up to me at Northwestern and told me I was throwing my whole life away because we would never detect gravitational waves and I would never be able to find a job. It was great. And I was supposed to join the nuclear physics lab instead. I'm glad that I didn't listen because since the first detection of gravitational waves from the binary black hole GW 150914, we have also detected a merging binary neutron star, and that's done through the LIGO Virgo collaboration, and several other detectors are potentially coming online soon to join the team. The LIGO Virgo Kagra collaboration will probably be turning on quite soon. But these are 4-kilometer long interferometer arms. Where did it go? There it is. Go all the way over here. Good. And the idea here is many, many, many galaxies away, binary black holes crash into each other. They emit gravitational waves with frequencies roughly at 1 kilohertz, and they make the gravitation or the arms of LIGO stretch and squash such that the lasers, which are normally perfectly interfering to let no laser light out of their detector here, they actually see the laser light. It's like a pretty standard Michelson interferometer. All right, since 2015, we're now at what's called the Gravitational Wave Transient Catalog 3. There are 90 binary black hole mergers in total, and there are 3 things that the LIGO collaboration is willing to say. There are only 3 astrophysical things, which is kind of funny. LIGO is like primarily a physics project for these people. They don't really want to think about the astrophysics, but this is what they'll say. So the first thing is that black holes with masses greater than 45 solar masses exist and merge with other black holes. I'll explain why that's interesting from a star perspective a little bit later on. They're also willing to say that the spin measurements that they can observe in their waveforms suggest the presence of multiple formation channels. What that means is that there is not one formation channel that dominates the entirety of their population.
What does that mean in terms of spins? There's low and high spins?
I will get to that. Yeah, totally. We'll talk about it. The spin stuff is tough going. We can just say that. The other thing that's interesting, and we're really starting to see as the populations get larger, is that observed parameters are correlated. So there is a really interesting correlation that's coming out suggesting that more lopsided mass ratios have higher spins. That's not particularly explained by anything yet, so I'm not going to go too into it, but we are definitely seeing, some correlations there. Okay, so as a theorist, the question is, where do the binary black holes come from, and what are the formation environments for all of these channels? The problem is that once 150914 came out, more black holes started rolling in, and the proposals for where the formation environments of these black holes came from started to outnumber the number of black holes that we have observed, because everyone has their favorite way to make binary black holes. I have deliberately not included citations here because the whole slide would be citations. There are literally hundreds of papers at this point arguing about formation channels. If you're not up to here in citations with this literature, the two things to keep in mind are that there are either dynamical ways to bring the binary black holes close together such that they merge in a Hubble time, or isolated binary systems. Oh my God, I'm so far off. Okay. So the difference between these two is really the formation environments. The dynamical formation is primarily going to happen in galactic centers, or AGN, where there's gas disks that are helping to bring them close together. In the centers of globular clusters, open clusters, or even in triple dynamics scenarios. On the other side, either the black holes are just luckily born close enough that they have just enough time to merge in the age of the universe from the primordial overdensities that were created right after the Big Bang. They could come from the very first binary stars. They could come from the standard binary stars like I just described to you, or they could evolve through something that's called the chemically homogeneous channel. Here, the stars are rapidly rotating enough that they don't actually expand to fill their Roche radii. So they have to start out very close together, such that they're very tidally locked, and they're spinning the stars up enough that the stars actually functionally mix themselves completely. And there's not a hydrogen, helium, stratification, but it's just fully mixed. Good. Okay, so these are all the ways to make them. The key here, though, if we want to actually find out where the binary black holes come from, is to put together a scheme to compare our simulations to data. And so what we do primarily in this field is we start out in the binary evolution case with some binary evolution theory. I come along and I put it into a population modeling situation. We look at the observed populations from LIGO. And then hopefully the observed populations tell us something dramatic about binary evolution theory. We reincorporate that in, and we eventually zero in on what the answer is. Spoiler, this doesn't work particularly well yet. The things, if we want to do this cycle, the things that we have to think about in our models are, what are the gravitational wave observables? How do they imprint themselves into our populations? So the first thing that gravitational waves is very, very excellent measure of is something called the chirp mass. This is a weird combination of the component masses of the merging binary black holes. This is what enters into the gravitational waveform. So we measure the chirp masses exquisitely well. We actually don't measure mass ratios particularly well, and that's because the mass ratio and the spin are tied together through spin-orbit coupling. The eccentricity, which is the ellipticity of the orbit, will imprint itself into the waveform, but since merging binary black holes have very, very short waveforms, and gravitational waves primarily shrink and circularize orbits, there's not a lot of eccentricity usually to play with there. And now this is where we get to spin. So this is actually what LIGO measures. Where did you go? There she is. LIGO measures this, chi effective. So chi effective is a mass-weighted spin of the components projected onto the orbital angular momentum. So we're not really measuring much about component spins at all. So Spin is tough with these things. There are some pretty obvious imprints, though, that we can look for in our environment from forward modeling. The first one is that in isolated environments, like those simulated with cosmic, we will never, ever, ever produce a black hole with a mass greater than between 40-ish and 60-ish. And the reason for that is because of something called pair instability supernova. For stars that are massive enough to produce a black hole greater than 45 solar masses, what happens is the star becomes so hot that the core is hot enough to emit gamma rays. These create electron-positron pairs randomly and emitting from the core. And then those electron-positron pairs take away a little bit of pressure, and the core starts to shrink a bit, and it'll create these either pair instability novae, where they eject massive amounts of mass off the star until they go below the limit, which is about 45 solar masses, or the core gets so hot that the entire star eventually just explodes, because once you create enough electron-positron pairs, the star contracts enough that you ignite oxygen. And if you ignite oxygen in a star, it's basically like blowing up the Death Star. There's literally nothing left. So there will be never, ever in any of our models, any black holes here. In globular clusters or dynamical environments, you can take two black holes, merge them together, make a bigger black hole. That's how you're going to get black holes with greater than 45 solar masses in the simulation. So this is potentially a very helpful way to tell whether binary black holes are coming from dynamical environments.
What's the graph? What do the graphs show?
This is just a mass distribution of binary black holes merging in the local universe from isolated binaries and from globular clusters. This is simulated data from our two
What's
codes.
the champion for so far for masses and black hole mergers?
So, that's a good question. So right now, the black hole masses primarily occur between 20 and 40 solar masses with LIGO. That's because of observational selection effects. You see the things that are farther away. There are black holes that LIGO has observed that are up in this region. So probably those came from dynamical environments, but not many. It's not the majority.
That's pretty amazing. They're that massive.
Yeah, it's super fun. Okay, good. So that's mass. We can also use spins. So if you make black holes a dynamical environment, the black holes are brought together from not the same system. So there's no imprint of what the direction of the spin of these black holes should be. That means if you take a collection of black holes from a huge population of dynamically formed binaries, you're going to get symmetric distributions of the chi effective here. That's a characteristic imprint from dynamics. In isolated binaries, we think that the spins should probably be aligned, but we have no idea if the spin should be high or low. For that reason, I mostly avoid spins altogether, because we just genuinely don't know how orbital or how angular momentum transport works in stars. So it would be full on garbage in, garbage out from my perspective. So I don't really touch spins very much. The other thing that I talked about was eccentricity, and I'm really excited about eccentricity because eccentricity is not just an indicator of dynamics, but it's actually the amount of eccentricity that you observe in a system is a direct correlator with how dynamically active that environment was. And so you can see this really nicely from a paper that Kyle Kramer wrote back in 2018. So what he's showing here is the 1 minus the formation eccentricity. So the systems in blue form with really high eccentricities. The systems, I've got it flipped, of course. I do it wrong in the talk. So this is 1 minus E formation. So these form with lower eccentricities, the red form with higher eccentricities. He then looked at what the eccentricity is when the gravitational wave frequency is about 10 to the minus 2 hertz. And the difference between each of the colors here basically shows you that isolated binaries which form in the galactic field, they have very low eccentricities. Binaries that form in globular clusters but are ejected and merge outside of the globular clusters form with middling eccentricities, but binary black holes that form and merge in the cluster, which is the most dynamically active way to form these things, have the highest eccentricity. So you can actually just measure how dynamically active the environment was of binary black holes if you can measure their eccentricities at lower frequencies. So this is potentially a fantastic way to measure things, but we're probably not going to be able to do this with LIGO. I'll talk a little bit more about that later. Okay, so these are the ways to measure things. At present, we can't measure eccentricity with LIGO yet. Spins are not well measured at all, so I don't touch them. But what we have done is we've looked at these mass distributions. Where did it go? Don't worry about it. Okay. So one thing that we've done recently with Case Wang, who is a machine learning magician at the Flatiron Institute, is build emulators, which use likelihood-free inference and normalizing flows to basically fit uncertain parameters in our binary evolution. That's what this alpha value is. And uncertain parameters in globular cluster formation, like the initial virial radius, and basically say, given LIGO data, what is the fraction of mergers that come from isolated binaries? That's what this blue histogram is. And what does that fraction tell us about the common envelope efficiency in isolated binaries and the initial virial radius in globular clusters? This is potentially pretty promising as we get more data, but you can see we don't really make like great measurements here. The fraction of binaries that form in isolated binaries is a really wide distribution. We're not really measuring stuff too well here. Our distributions here are basically useless. We don't measure alpha. Like it's not so great. It actually gets worse. So at the same time, Mike Zevin did a similar type of study where he included a bunch of different assumptions. That's what all of these little colors are here, to measure the relative fraction of, say, common envelope and globular cluster formed binary black holes. And if you add formation channels, you change your answers by about a few orders of magnitude. So like, what are we doing? You basically, if you're going to make these kinds of measurements, you have to be absolutely certain that you've got all the formation channels, because if you don't, all of your measurements are bunk. Cool. It gets even worse. Cool. Okay, so this is a really fantastic study from Flor Brokgarden. This is the culmination of something like 270 binary population synthesis simulations. She did it for merging binary black holes on the top, black hole neutron stars in the middle, neutron star on the bottom. Every set of points is a different set of assumptions for binary star physics. Every one of the vertical lines is a different set of assumptions for how the star formation history over the age of the galaxy can change based on metallicity. You can see that where are we? Down here. The double neutron stars are less sensitive to the star formation history because those lines aren't really spread out. Systems with black holes in them are extremely sensitive to the star formation history, and the reason for that is because black holes come from very massive stars, and very massive stars can have very different wind strengths depending on their metallicity. So if we get the metallicity-dependent star formation history wrong, we get the binary black hole merger rate wrong by literally orders of magnitude. So things are like tough. It's like we finished a conference in Aspen in January, and everyone literally was like, should we like pack it up? Like, what are we doing here? There are pathways forward. Those pathways forward, I think, they come on different timescales. So I'm going to walk through each of these. The first one is thinking about multi-band gravitational wave observations, and we can go there. I want to quickly say it's probably not 15 years. I hope it's more like 10. The way that we're going to do this is we're going to think earlier in the phase of these mergers. So LIGO measures things at 1 kilohertz. Binary black holes probably aren't forming at a kilohertz. They're probably forming at wider orbits, shrinking and circularizing. If we had a detector that could observe things at millihertz, we might be able to learn something. So what's this detector? This detector is called LISA, the Laser Interferometer Space Antenna. The planned launch is like something like 2035. It's like long time scales, but it's a space mission. Space missions take a long time to build. Things are really ramping up inside of ESA. LISA is not like totally a farce. I'll just say that. Like it's definitely going to happen. Whether or not it happens in 10 years or 15 years is the question. Good. Okay, so LISA is very different from LIGO. It's an equilateral triangle. It has spacecraft that are about the size of a bus, and they are spaced 2.5 million kilometers apart. It orbits in a fun like moonwalk cartwheel orbit that is Earth trailing by about 20 degrees and inclined to the ecliptic by 60 degrees. It is sensitive to orbits of roughly 90 minutes down to 20 seconds. So very different regime. When we talk about detecting things with LISA, we use something like this. It's called a sensitivity curve. We don't collect photons, we collect stretches and squashes. The shape of the sensitivity curve, so this is going to be basically how much gravitational wave power is radiated from the system. This is the noise curve that says if you're above here, you will be detectable by LISA. The shape of the curve down here is basically how well can we measure the position of test masses that exist in those spacecraft. We have a noise floor that's basically how well we can keep those test masses isolated from things like solar radiation pressure. And as you go to higher frequencies, the sensitivity degrades because the gravitational wavelengths are smaller than the size of the detector. And you can see that in this fun beating pattern here, which actually shows harmonics of the size of the detector. It's kind of a fun physics thing. Okay, so basically every single gravitational wave merger that crosses into LIGO goes through the LISA band. So these are potentially detectable systems that LISA can observe. We can do things like Alberto Cezanne did in 2016 and take the rate of binary black hole mergers that happens in LIGO and wind them backwards in gravitational wave evolution to see whether or not they'll be detectable by LISA. If you do that, you get something like 10 to 100 systems that we expect. The uncertainty here is whether or not those binary black holes form with eccentricity. So that's cool. You can also do things like I have done and many others have done, where you forward model the population using population synthesis studies, where you say isolated binaries will make binary black holes at this rate. And we get wider uncertainties because we don't know where all these binary black holes from LIGO are coming from. Maybe they're all coming from globular clusters and there are none. So it's possible. Cool. One of the things that we studied very close to when 150914 was detected was what does the eccentricity of binary black holes look like in the LISA band? So what I'm showing here is a figure of eccentricity on the y-axis, gravitational wave frequency on the x-axis, and every single one of these lines is a binary black hole that was formed in a simulation, either in an isolated binary, that's pink, and goes through a common envelope, an isolated binary that doesn't go through a common envelope, that's the teal, or in a globular cluster, and that's the dark blue. So every line is a black hole. Where they start at the top is what they form with. So they form with a high eccentricity, gravitational waves shrink and circularize them, moving them towards the bottom right. The LISA band is highlighted between 10 to the minus 5 and 10 to the minus 1 hertz. And I've got this white vertical line here. The reason for that is because every single binary black hole that exists there will have a measurable orbital evolution during the LISA observation time, and that means that we can tell that the orbit is circular or eccentric based on how fast it shrinks, because eccentricity drives that. Whether or not the eccentricity is large enough to be detected by LISA is determined by these two lines. So there was a parameter study by Nishizawa in 2016 that basically found that above 10 to the minus 3, so 1 part in 1,000 eccentricity, their synthetic LISA was able to resolve 90% of the eccentricity measurements, and above 1 part in 100, everything was measured. So any system, where did she go? I don't know where she is. There we go. That's in that quadrant up there has measurable eccentricities. Anything below it is just going to be measured as circular. But still, we could measure eccentricities. Great. Some of them may be observable. It's way more exciting if you also think about the fact that above this white line, for systems which we measure observed orbital evolution, we're also going to measure mass. And when you look at the population simulations, everything splits out beautifully. So when LISA flies, we won't have a question of where the binary black holes formed. We'll know they were dynamically or isolated formed, just right off the gate. Cool. That's going to happen in 15 years. What about before that? I have to do work between now and then. Okay, so the next thing that I think is actually very exciting and is a different departure of what we've been doing is looking at targeted modeling of individual events. So here, I showed you the blue curve. We do our forward modeling. We assume that binary evolution theory goes into our population modeling. We compare to our observed populations. Fine. What Kay Zhuang and Will Farr and I decided to do while we were sitting in a bar in Aspen being super depressed about the state of our field was think about ways that we could turn this on its head. And so instead we thought, let's start with the observed populations and do a population study on every single binary black hole, treat them as bespoke systems, see what that tells us about binary evolution. And we just barely put out a study that more or less does this. So we did a pilot of GW 150914. The top right shows our reprojected, basically, mass measurements. And so what we did here is we basically started with LIGO posteriors in mass and said, we are going to let all of these different parameters that are in my giant corner plot, which are uncertain binary evolution physics, we're going to let those float across totally insane, like physically probably not realistic ranges, and see what can produce a gravitational wave event that makes a 150914 in a Hubble time. So we mapped the gravitational wave event masses onto the initial, the zero-age main sequence masses, zero-age main sequence orbital eccentricity and period, as well as metallicity. And then we also jointly model Roche overflow outcomes and see what's possible. So there are some things that are interesting, and these are the black squares. That's what the top three guys are up there. Some things to note, not every ZAMS mass can make a 150914. So we found things that can't make it, which is nice. That actually tells us something real. There are only a certain number or a certain range of masses that will make a 35 plus 29 solar mass black hole. That's like actually a real statement, which is crazy because we haven't made any real statements from isolated binaries since then. Another thing that we see that's an interesting feature is this massive vertical line at 80 ZAMS mass. This FAC is how much accretion, how much mass is accreted through a stable Roche overflow. So if you're in a stable Roche overflow, the donor is sending mass through L1, and it can be accreted by its companion. If the FAC there is 1, that's a perfectly conservative mass transfer. If it's 0, it's perfectly non-conservative. At 80 ZAMS solar masses, we make no measurement at all. And we were like, what? Like there's no correlation at all. And it actually turns out to be because at 80 secondary masses, you also have 80 primary masses. And so these systems are actually double core common envelopes where they never go through a stable mass transfer. There's no way for them to do it. So in our study, we basically found that finding something that is uninformative actually tells you how those systems were made. So finding that we don't measure anything in the accretion efficiency means that accretion efficiency isn't the channel. So it's kind of like a weird backwards puzzle game that we're playing with this stuff to just basically see what is and isn't possible. A better illustration of this, I think, is looking at just in detail what our simulations look like in comparison to the standard way of modeling these populations. So the standard way of modeling these things is to pick fixed values. Pick a fixed alpha and a fixed FAC, and then we vary alpha and see, does alpha change this a lot? Like how do things change? If you do that, you can see like similar trends. We still see this like double common envelope business here at 80 plus 80. But if you let everything vary, we actually map out the parameter space that is impossible in our models to make. Whoa, it didn't get all the way over there. But in the black box, we map what can't be done, which is something that we can say now for every single system. And so we're really excited about hopefully using this to simulate the entirety of the catalog and actually look for overlapping trends that start to come out from all of the 25 solar mass black holes that LIGO has found. We might actually be able to say something that's more along the lines of isolated binaries will not make these things, so we should stop trying to do that because we literally can't in any of our models. We did a tiny pilot to just look at some trends, and they do start to kind of come out. One thing that we're seeing a bit, but we're nervous to like really plant a flag with, is that this accretion efficiency, so how conservative the mass transfer is, appears to be correlated with the gravitational wave mass. This makes sense from a first principles stellar evolution perspective, because the more massive black holes you form, the more massive stars you have, and the more massive star you are, the more mass you can accept from a donor. So this seems to be working fine, but watch this space because it's really, really nascent. Like paper is still under review. Good. So that's one pathway forward again. And the last one that I want to talk about is something that I'm like super, super excited about. We just had a press release for this, I think, at the beginning of the week. And that's complementary population, so not gravitational waves at all. Now we're like thinking about light. So I showed you this whole phase, and all I've been talking about are like the mergers at the end. There's a lot of stuff that's like shining in earlier phases, and we have these things that I've seen many of today called telescopes that are looking at these things all the time. So maybe as a theorist, I shouldn't be only constraining with the very, very end states. And instead, I can think about very specific states of stars that we should see quite a few of in our galaxy, and we do see quite a few of in our galaxy. As a theorist, what I think about is that as they go through a more advanced evolution, their orbit sizes change. That means the way that I observe them is also going to change. So at the very, very end states, we're using gravitational waves like I've talked about. If they're in this accreting, say, black hole plus bright star phase, they're obviously going to be things like X-ray binaries. But if they're in detached states, there are a whole host of surveys right now that are out there looking for binaries with stars, namely photometric, astrometric, and RV surveys. So something that I've been working on quite a bit are these things that Karim El-Badri has termed dormant black hole binaries. Why are they called dormant? It's because they're not accreting anything, so the black holes and the environment around the black holes isn't shining. All you see is the motion of the bright companion. So one way to do this is to find them through radial velocity surveys. You measure a radial velocity. It tells you something about the mass of the luminous companion, the mass of the black hole, but there is this annoying inclination uncertainty that arises. So if you're looking to find candidates of bright stars orbiting black holes, you measure something like this mass function, but there is that inclination degeneracy, which has proven to be very annoying for people searching for these things. There's another way to do this, and that's to use astrometry from the Gaia satellite. Astrometry is lovely because this, let's see, here we go. The luminous companion separation is literally the astrometric projection of the orbital motion that Gaia observes. And in this case, we can measure direct black hole mass measurements without inclination degeneracies. So that's cool. We realized this quite a while ago in 2017 and have spent the past few years thinking about what the Milky Way population of dormant black hole binaries looks like. So for our most recent studies, we've combined cosmological simulations from the Latte suite, which tell us where all of the stars in a Milky Way-like galaxy will form, what their metallicities are going to be. We use Cosmic to make the black hole binaries, and then we apply the standard Gaia orbital selection cuts. One thing that we find is that basically every binary black hole, not every, most binary black holes that Gaia will be sensitive to are post-common envelope binaries. The reason for that is twofold. First, the orbital period that Gaia is sensitive to in this set of figures from a bunch of models, this is from my paper in 2017, Gaia is the region that's shown in yellow. And the orbital period that Gaia is sensitive to is basically all post-interaction binaries. There are the two like swaths of systems in each of these figures. And those two swaths basically show you two different orbital period distributions. The larger orbital period distribution are systems which haven't interacted. They're in wide enough orbits that they don't interact. Great. So that's one way to look at it. The other way to look at it that we looked at in our most recent paper, that should be 2021, not 2017, sorry. We looked at the orbital period distribution and just counted how many black hole plus main sequence stars and how many black hole plus post main sequence stars went through a common envelope that are below this orbital period cutoff. And the vast majority are common envelope systems. So Gaia is sensitive to post-interaction binaries. That's cool. We can also just count up how many we expect. Chirag did some lovely work to count, and we basically predict something between 40 and 290s in the next Gaia data release. We have Gaia DR3, so I'm going to zoom past this to talk to you about actual data. So right now there are two slam dunk dormant black hole binaries so far. The first one came from the VFTS survey that's done in the LMC. The reason that I'm showing you this tweet from Kareem is that Kareem has been the field's black hole candidate killer for the past 2 years. He's killed about 7 candidates so far by looking in their spectra and finding bright companions to the black hole, what that should be the black holes. So Kareem is a fantastic spectral modeler, and literally several surveys have put out like, this is a candidate, this is a candidate, this is a candidate, and then Kareem comes in about 2 weeks later and says, this is not a candidate. So he endorsed this black hole. It's called VFTS 243. It was put together by a team led by Tomer Shinar. It's in the LMC. It's got about half solar metallicity. It's kind of like an analog to SIG-X1 a little bit. Like it's just on its way into being a SIG-X1. The other one that I actually want to talk about, this one was found through a radial velocity survey. The one I want to talk about that was just had our press release on Monday was a sun-like star orbiting a black hole. This was actually detected by Gaia, so it's called Gaia BH1. And this is a really weirdy system. And I'll tell you why. It's a 10 solar mass black hole orbiting a 1 solar mass star. It's at about 185-day orbital period. It's quite eccentric, and it's just a little bit subsolar. One thing that's quite fun about this is that the size of the orbit is basically an AU. So if you were to put that G star where the sun is, the black hole sits where the Earth is. So that's fun. The other thing that's quite interesting is that the G star is super boring. There are no features. You could almost put it literally where the sun is and people wouldn't notice. Like it's just so normal. Okay, so Kays and I have our fun targeted modeling approach. And so we modeled the hell out of Gaia BH1, and we mapped all the possible combinations of ZAM's binary parameters, common envelope efficiency, and natal kick strengths to see how does Gaia BH1 form in binaries. And what we found pretty immediately is that first, we know that the 185-day orbit and the mass of the black hole absolutely requires a common envelope evolution. There is no way that the black hole progenitor could stably transfer mass onto such a low mass star. There is no way that that star could fit inside of a 185-day orbit, so common envelope was the only way to do it. If you're going to do this, it pushes our ZAM's masses, though, to be completely crazy. So our ZAM's mass that we fit out of our models is 70 solar masses, and our secondary mass, that little G star, is of course 0.9 solar masses. It doesn't change. This is probably not realistic in any sense at all. The reason for this is because the 70 solar mass ZAM star will have done its whole thing very quickly, and the 0.9 solar mass G star is still like thinking about contracting to the Hayashi track. So like, we really don't think that that's particularly physical. Some other things that really make this stand out as quite bizarre is that the eccentricity in the orbital period enforce a very extremely efficient envelope ejection in the common envelope. So the way that you measure this alpha common envelope is you basically say, we're going to take orbital energy, we're going to dump it into ejecting the envelope, and how much the orbit shrinks is going to be multiplied by some efficiency factor that's required to unbind the envelope. An efficiency factor greater than 1 means that you are somehow adding energy to the orbit in some way. An efficiency factor of 13 means that you are adding 13 times the orbital energy to eject the envelope. And so when we fit this, we were like, okay, like this is probably not realistic. The other thing that we find here, just to be complete, is that we can measure the kick strengths actually very, very well in this scheme. And that's because the eccentricity and the orbital period basically define how strong that kick strength can be. So we see some nice, fun things. First, we see that the kick had to be pretty low. That's not so surprising. It's not unbound at 185-day orbits. We also see some fun things like the kick angles and strengths are correlated. So at that very low kick strength, that's in the direction of the orbital motion. So we know that our scheme is working pretty well. If you're going to have a higher kick, you have to be working against the orbit, which is fun. But the punchline is Gaia BH1 completely challenges standard isolated binaries. And so we were pretty rapidly able to say, this one is not an isolated binary. There's no way. The 70-to-1 ZAMS mass ratio was crazy already. The common envelope ejection was even more crazy. And so people should start looking at other formation channels to make this. There are several that people have suggested. Hierarchical triples, maybe, who knows, that's a huge parameter space. Open clusters could do it. Maybe that's a way to do it as well. We're working on that, but it could be something else. So the nature of Gaia BH1 is still a bit of a mystery. It's kind of a bummer that the very first one that we found wasn't one that I could do something with binary evolution with, but that's okay. And with that, I'm just going to leave some takeaways. So first, if you're interested in binary populations at all, or you could use things like delay times for supernovae or merger times for white dwarfs or whatever, Cosmic is a great and flexible tool to do that. I'm happy to talk with you about ways to incorporate that into your workflow. Binary black hole merger formation channels will not be solved in the next 5 years, I don't think. But we're making headway. We're getting there. We're learning things. It's not a total loss. And finally, watch the space of dormant black hole binaries. These things are a really unique opportunity, and they're gonna start falling out of the Gaia data in the next data releases, as well as the RV binaries. Thanks.
Yeah, how much, so you get the common envelope thing and the black holes inside the envelope of another star.
Yeah.
How much can you grow the black hole just by accretion in there?
Yeah, that's a fun question. So it depends on how long the common envelope happens. Morgan McLeod has done some work on this with like wind tunnel simulations where he basically plunks a black hole inside of like just gas as it goes by and kind of like mimics common envelope. The black hole doesn't gain more than a fraction of a solar mass at best, even letting it run for 10 to the 5 years. So to get any sort of appreciable accretion in a common envelope event, they have to last really long and they have to be extremely super Eddington accretion. So probably the answer is no, like none at all.
But do you know, I mean, how do you know the gas dynamics inside a common envelope? Like, I mean, you know, if it's an isolated black hole, it's going to get an accretion disk and whatever.
Yeah.
You know, if you're inside another star, there's going to be some weird stuff going on.
I still think Eddington luminosities like matter though. And I think that's what stops Morgan's wind tunnel simulations from accreting a lot of black holes, is that Eddington luminosity that just pushes things back out. Those wind tunnel simulations too, I think, are really, really optimistic because it assumes that it's happening for like many, many, many thousands of years. So the prevailing knowledge is probably not. Of course, yeah, no, actually, I don't think it could do it. That's what we think. I'm trying to think of it. I don't think it'll work. You are absolutely right, though, that like we don't know how common envelope works. So who knows? There could be extra internal energy in the envelope. Like there could be crazy stuff, but just in the current status, answer's no.
My question is, so in the last part of your talk, you mentioned that you have some efficiency of 13.
Yeah.
Can you give some more intuition as to how you measure that?
Yeah, totally. Where did the cursor go? Is it over there? I'm gonna go to the left as far as I can. Good. A different way to think about this is here. Okay, so when a star goes into Roche overflow, it's got some radius, and it's going to have some amount of binding energy. If you go into a common envelope at the biggest that your star's ever going to get, you're minimizing the binding energy. That's why our orbital periods are so high here. So the code is basically saying we're going to take the black hole progenitor and put it into a common envelope, into a configuration such that it goes into common envelope in the widest possible orbit that it could, so that it's the least bound. And then when we go to here, that means that this initial orbital energy reservoir is enormous. The binding energy is as low as it can be. And then we basically just say the final binding energy has to be pretty close to the current, or sorry, the final orbital energy has to be pretty close to the orbital energy that gives you the current orbital period, more or less. And so that's how we just basically match our alpha. So it's like, it's bordering on just phenomenology of asking what is the initial period that gets you the widest possible orbit going into common envelope so that you can have a wide enough orbit coming out of the common envelope. And even though we can't get there, how big do we have to make our alpha so that it can fit? Huh?
It's driven by the period.
It's driven by the wide period. If the orbital period was not 185 days, but was like 18 days, I wouldn't have been quite so like, this is definitely not it. Our alphas would have been fine, maybe two, something like that. So it would have been much less of a struggle. But the 185-day orbit really, really hurts us from the isolated binary perspective. Yeah.
You had a plot where you showed, if you look at alpha and f act parameter sort of vary, you can set a really like cool constraint on the total parameter space. I'm kind of curious as to like how strong that constraint is. So like if you detected something outside of it, would that be like, oh, we just need to tweak our theory a bit to encompass it? Or would it be like, wow, it's a red flag, like the measurement must be super off? Or
Yeah, I mean, this measurement up here, I would argue this guy is like an inkling at best. Like, it's not a very strong measurement. We basically cover, if you look at like the 90 percentile, like you cover the whole box. If we actually start to see really defined shapes, like say this mass one, where did she go? There. Whoa, it's too close. The mass one. That's something where I would start to make like stronger statements. The time where you really start to make strong statements is if we have binary black holes that appear to be somewhat similar and we model them the same way and we get the same answer for many of them going in, like coming out of our simulation. So it's not so much we make a very strong statement from this one system, but if we can make the same statement for every system in the catalog, that's more robust. Yeah. We'll see. I think that this is promising, but maybe not the next, like, we're not going to solve everything with it. Yeah.
So,
Any other questions?
it's just,
Please go ahead.
I kind of had your question. I was going to say, how can we do a back of the envelope calculation for the MDOT because I thought I should be able to think through this, but I don't know. I could, I mean, you have ram pressure, of course, that's opposing the radiation pressure.
Yeah.
That subjects people talked about for a long time, the foreign ship objects.
Yeah.
Has anyone really calculated how fast that mass might grow, or what would happen for that?
I think it's a similar idea that
But it's
the
been around so long, I figure someone must have.
yeah.
But
Yeah,
we
yeah,
still know
that's
nothing about that.
we basically what we learn from what studies have been done are dropping compact objects into wind tunnels.
Why? I'm gonna look up the original Thorn paper.
I mean, yeah, that's like the 60s. But yeah, I think the standard prevailing wisdom is that they're not accreting because of Eddington luminosities. So I think the other thing to think about though with that is if it's a neutron star in there, a lot of people think that neutron star can accrete enough to collapse, but then is that a direct collapse? Maybe not, maybe it is, I don't know. But I think those are even more uncertain than black hole common envelope, which is crazy to say.
It's not obvious to anyone else either, but
Yeah. Yeah.
We're just a little bit over an hour, so let's have one last question. Yeah.
I was going to ask, when you were talking about multi-band observations,
Yeah.
Gravitational waves, you're referring to observing different systems in those different bands, not like the same system in both like the LIGO and LISA band?
Kind of both.
Both?
Yeah. So that's a fun thing. That's why Alberto got a PRL out of this paper. Is he basically said, "Hey guys, guess what? If LISA had flown when we said it was going to fly in 2010, it would have seen 150914. Like totally would have seen it, and could have actually predicted that it would merge in LIGO about a year out, and could have predicted within minute timescales when it was going to merge." So we think that there are probably, if you're optimistic, you think that there are going to be 100 LISA sources. Maybe 10 will be these multi-band traversing systems that go across in about a year.
Like that's the time scale, about a year?
Yeah. So this time scale here is the merging time scale for 150914. Yeah. So that could be super, super fun. It's only going to be above maybe 15 solar mass systems that are going to do that traversal. The vast majority of the LISA sources are going to hang out at these lower frequencies, but even still, getting those lower frequency guys will be super exciting too. Yeah.
How much money does LISA cost in 2022 dollars?
In 2022 dollars, that's about $2 billion.
That's all.
I know. Oh my God, you're the first person to say that. Call someone up and say that to them.
It's good LSD. You gotta add the factor of 8 or something.
Yeah.
to whatever,
That's
but-
this is so what oh man, let's talk about politics. LISA is like really stable engineering dev though. Like LISA's TRL status is like where James Webb was like 3 years ago. Like they're using super old lasers, they're using super old like tech for everything. So they could start bolting it together, and Pathfinder showed that it'll work now.
Yeah, that's true.
Like it's really, it's not folding up mirrors or anything like that. It's literally just like get the damn spacecraft up there and start it, because it's really, really stable. Yeah.
Awesome. Thank you.
Thanks.
Take snacks with you.
I was just wondering what is the precision of the LISA?